So in the last video we defined the sum of squares and we derived why we use this notation, and we explained a little bit of why we're going to use it in the future. But before we do that, I'm going to rewrite these equations in more ugly forms, so to speak. But this is also useful for manual computation. So if you didn't have like a computer or some sort of program that can do this calculation for you and you had to use a calculator, we could rewrite this in an equation that makes the calculation easier by subcategorizing the calculation by, like the sum of xi and then doing the sum of xi, yi, or something like that. That simplifies this calculation, because if you do this, you're going to have to take each point minus x bar, square it, then do the next point, and it gets tedious. Rather, you could do like 4 main calculations and get the same value. So we're going to basically do all algebra today, no calculus or anything like that. We're just going to manipulate these equations to get some other form of this equation, or this equation, or this equation. And it's also useful to see these other equations, because these different forms of sum of squares pop out in the derivation of linear regression lines, which we're going to do in a future video. So I just want to get you familiar with these different notations. So just bear with me, I'm going to do a lot of algebra and basically little tricks of how to see these equations. So we're going to start off with xi and x bar. Since generally this equation is basically the same equation as this, we could just solve this once and then write the same form in terms of y, because these are basically the same equation with different variables. So we're going to start off with xi and x bar. So we're going to rewrite the sum xi minus x bar squared as xi minus x bar times xi minus x bar. And what we're going to do is distribute these values to get a new form of this equation. So what we're going to get is the sum of xi squared minus 2x bar xi plus x bar squared. So that becomes a more simple equation to work with, and the property of summations is that we can distribute this summation to each term. So we can rewrite the following equation as this: xi squared minus 2 is a constant, so we're going to move that out, times x bar xi plus the sum of x bar squared. So an important thing to notice is that x bar is also a constant, because we're assuming that we have n data points and we're not adding more data points as we do this calculation. So we're going to say x bar is constant and actually move this out of the sigma notation. And we're going to do the same thing here, but this time it's x bar squared. So we get this following equation, and we get this sigma by itself. And basically that means you're just doing the iteration however many times that you defined it as. In this point we have n data points, so we do the iteration n times, so it's like adding 1 plus 1 plus 1 plus 1 and doing that n times. So really you could just simplify it by multiplying 1 by n. So we can rewrite this following equation as follows: xi squared minus 2x bar xi plus n x bar. And just because I don't feel like I was clear about that, I'm going to show you right now. So let's note that this can be written as this. So we could say x bar squared is the sum of I equals 1 to n times of 1. So we're gonna add 1 n times. So we're gonna, sorry about this. This is really sloppy. 1 plus 1 plus 1, and we do that n times. So we can rewrite this equation as simply x squared times sigma as n x bar squared. Hopefully that makes sense. Sorry for this ugly mess right here, but we could continue with our new form of the sum of squares. So using this idea, we could rewrite this following equation as follows. So now we're going to define x bar. So define x bar as follows. So the reason we want to define it in a new way is because we want it in sigma notation, so we could do some manipulation of this equation. So we could define x bar as simply the sum of the xi's over the number of data points, so n. So we could rewrite this average in terms of sigma notation, and what we're going to do is we're going to plug in this notation into x bar in the previous equation. So what we get is that we get the sum of xi squared minus 2 times x bar, which is this, times xi plus n sum of xi over n squared. So I basically plugged in the average value in terms of sigma notation in this following equation right here. So now that we have that, we're going to simplify this squared term. So we're going to do the following. So this equals the sum of xi squared minus 2. Since there's two xi values being multiplied, this is simply the sum of xi, the quantity squared. So we're going to do sum of xi squared over n, and then I'm going to distribute this squared to each term, the numerator and the denominator. So we're going to have the n times the sum of xi squared over n squared. And what's nice about this is that this n cancels out with one of the n's in the denominator. So what we can rewrite now as the sum of xi squared minus 2, the sum of xi quantity squared n plus sum of xi quantity squared over n. And since this is this term is the same as this term, or they're like terms, we could basically add these together. So 2 is a coefficient here, a negative 2 is a coefficient, and this is a positive 1 coefficient. So we could simplify this whole equation to the sum of xi squared minus the sum of xi quantity squared over n. So this is the new notation for the sum of squares. So this equals the sum of xi minus x bar squared, which is very useful to use. And by the way, this is not a quantity squared. You take each xi value, square it, and then add it. This one you add up all the xi values, then when you get that total sum, you then square it. Alright, so this notation is not the same as this notation. This is completely different. Okay, so this is the new notation, and why I was saying that this is manually, computationally easier is because that in this way you have to do the deviation, then square it, and then go to the next point, do the deviation, square it, and then do the next point, and so on. This way you only have to do one sum. You take the square of all x values, add those up, take that sum, which is, I think, more straightforward and less tedious than doing this, and then you add up all the x values, and then square it, and then you divide by the number of data points that you have, or how many x values you have. So that way you do 3, kind of tedious calculations, and then do one big final calculation, instead of doing, n deviations and then squaring them, and then, this seems a lot easier to do by hand. But if you're using a computer or writing a program, this is actually, it doesn't really matter what notation you use. But this is more, by hand, computationally easier. So we can now redefine our two following sum of squares. So we found a new form of this notation for this notation and this notation. We because these values or these formulas are basically the same thing but with different variables. So we could redefine the sum of squares for y and x as follows. So we have those two different notations for xx and xy. So we have these two different notations now, which I'll show you right quick. So we have sx in terms of this notation and sx in terms of this notation. And these notations come out in derivations we'll use later. So I want you to get familiar with this new notation. So now we're going to redefine this sum of square, which is a little bit more complicated, but you know, the same process still follows. Maybe you want to give it a chance to give it a try to find that new form, but it's basically the same steps, and I'll go through it right now. So sxy can be written as x, the sum of xi minus x bar times yi minus y bar. And we're going to do the same process all over again, but in terms of this equation. So to start off, we're going to distribute this quantity, this binomial, these two binomials. So we're going to do xi minus x bar times yi minus y bar, and that's simply going to be this. So let me say xi yi minus xi times yi minus y bar times xi, and then we're going to do x bar yi plus x bar y bar. So that's our new distributed two binomials. So now that we have that, we can now do the same thing. We're going to distribute the sigma notation to each individual term, and we're going to manipulate each individual term by on its own. So we could rewrite this as the sum of xi yi minus the sum of y bar xi minus the sum of x bar yi plus the sum of x bar y bar. So as before, x bar and y bar are constant, so we can move that notation outside the sigma notation, or outside the sigma. So we could rewrite the equation as follows. So we get the sum of xi yi minus y bar sum of xi minus x bar the sum of yi plus x bar y bar times sigma. And as we said before, this just simply becomes n times x bar times y bar. So we further can rewrite this equation as this. xi yi minus y bar xi minus x bar yi plus n x bar y bar. And again, we're going to redefine x bar and y bar in terms of sigma notation. So we're going to plug this notation into this equation, and we'll see some simplification occurs. So the sum of xi yi minus y bar, which is sum of yi over m times xi, minus x bar, which is the sum of xi over n times the sum of yi, and then we're going to do n times the sum of xi over n times the sum of yi over n. So now that we have that equation, now we can simplify this quite easily. So first thing we're going to notice is that these terms are the same. And we could add these terms together, so we get negative 2 times this term. And then here we have an n cancel out with one of the denominators, and we get another term that equals this term. So we could rewrite the equation as xi, yi, minus 2 sum of xi, sum of yi over n, plus one of the n's cancels out, so we get sum of xi, sum of yi over n. And what's nice about this is that minus 2 plus 1 of these cancels, so we get the sum of xi, yi minus the sum of xi, sum of yi over n. So that is another notation for sxy. So sxy is simply xi, yi minus the sum of xi, sum of yi over n. So that is our new notation for the following sum of squares. So this is the new notation for sxy, which we see here. We put it like this. So as you can see, this right here is the same as this. And then earlier we showed that these terms can be written in a very, very similar form of this, but in terms of x or y only. So the purpose of this video, again, is just to get you familiar with this different notation, because this is going to pop out in a derivation of linear regression lines. So this is the following two videos that I've done is just to build up for linear regression, which is what we're going to do in the next video, I believe, or in a future video for sure. So that is what I wanted to show you guys, get you familiar with this new notation of the sum of squares. So in the future video, we'll show you why these values or these different formulas are important.